So the topic of today's lesson is going to be Unit 1.3, which is Day 2, which we're going to focus on geometric sequences today. So we've kind of already looked at some of the vocab and what a sequence is and how a sequence progresses, but today we're going to look at a geometric sequence in particular and how that works for us. And then so our overall objective today is that you're going to be able to write the recursive and explicit formulas for a geometric sequence and then be able to find what we call our nth term, which is kind of this unknown value that we'll have that kind of represents any number. So it could represent 1, 2, 3, and so on, or even the 151st term if you want to think of it that way. But that's really what our objective is, to do these two things and write those two formulas for our sequence. So the first thing that we need to do is we need to recognize and kind of go over again what a geometric sequence is. So we've already looked at arithmetic sequence that deals with addition and subtraction. And so a geometric sequence is an ordered list where the common, or what we call constant, ratio between consecutive terms is always constant. And so that's really the kind of the thing that we're looking for, is that it's always the same. As we looked at our arithmetic sequences, we wanted to look to see that we were adding or subtracting the same thing. But this time, when we think of ratio, like I told you before, is think of a fraction. But what we're really going to be focusing on is multiplication and division. So we're going to look to see if there's multiplication between terms and division between terms. So let's look at this example that we have down here. We have 5, 15, 45, 135. And so we need to be able to find this constant ratio if it exists. It's not as easy as looking at two values and seeing if they're adding or subtracting every time. And so there's a way that we can do this, and we can do it for anything that we want. So we basically take the value of a term that we want, and we're going to divide it by the previous term. And so what that's going to allow us to do is set up a fraction of two values. So for example, what we're going to find is we're going to find this constant ratio, and we're going to call it little r for ratio. And so we're going to look at two values. Let's look at 5 and 15. Now I'm going to take a term and divide it by its previous term. So what I'm going to do is I'm going to take 15 and divide it by 5. So notice that I didn't choose 5 and divide it by 15, because that doesn't give me an accurate account of what's actually happening. I always want to take the next term and divide it by its previous term. So when I do this, I get a value of 3. Now, in order for me to make sure that this is the same every time, I now have to do that for the second pair. So I'm going to take 45 and divide that by 15, which is also going to give me 3. And then just for one more, I'm going to take 135 and divide it by 45. And of course, you might have guessed that it's also going to give me 3. So the idea is that my constant ratio in this case is going to be 3. Now we can also think of it as being times 3, but we can kind of eliminate the whole division thing and use fractions, which I know some of you might be a little scared about fractions, but it's really not going to be that much different than what we just did here. And then so by using this kind of fraction here and this little two-step little fraction that we would have, we can find our constant ratio without too much difficulty. And so now we're going to be able to use this geometric sequence and find the next two terms. And so we have a couple things that we carried over. So the first one is that we had our constant ratio of timesing by 3. And so we're going to introduce our recursive formula for geometric sequences. And so this is going to be very similar to what we did for arithmetic sequences. So we have a sub n, so any term would be a sub n minus 1. And then we're going to times that by our constant ratio. And so really the only difference between this and our arithmetic sequence is that we're using multiplication rather than using addition or subtraction. So we take the term before it and then multiply it by our constant ratio. So if we're going to combine or find the next two terms, we're going to take 135 and then multiply it by 3. And so that gives us a particular value of 405. And then if we take 405 and then multiply that by 3, then that would give us 1,215. So the idea is that we can find any term, and this is, like I said before, this is the way that we would be able to kind of intellectually think about this and use our intuition to say, oh yeah, we just keep multiplying by 3. And then that's exactly what the recursive formula does. It just helps us create a list, and then we could just keep going on and on with this as many times as we needed to. And so here's just a couple examples of doing that. So we're going to find the next two terms, and then we're going to write our recursive formula for that. So as far as finding the next two terms, we can do this a couple different ways, but either way that we need to do this, we need to find our r. So we need to find what that ratio is. And so I'm going to take these two values and not necessarily look just for what I'm multiplying, because it might not be as clear. What I'm going to do is I'm just going to take these two values, divide them, and it gives me 2. Take the next two set, divide them in the same way, and that gives me 2. So I know that my r is going to be 2. And so if I was to fill this out for the next two terms, I would take 8, multiply it by 2, which would give me 16, and then multiply that by 2, which gives me 32. Now when I write my recursive formula, all I need to have is r. So when I plug this in, a sub n, that always is the same, is equal to a sub n minus 1 times 2. And so we just kind of build our recursive formula that way. Now the next one isn't as easy, and so when we look at having fractions, we don't have to think about this being something completely ridiculous or something that we don't know how to do. Now we could take this very easily, like I said, take 2/3 and divide it by 1. And if we remember how to divide fractions, we always multiply by the reciprocal. So it would be 2/3 times 1 over 1. And so what that would give me is negative 2/3. And so that would be my r. Now I could check that to make sure that's the same. Now another way that I could do this is, if you notice, these are alternating from positive to negative, back to positive, and it's probably going to go back to negative. So I know at least my r is going to be a negative value. But what I can do is I can also set this up so that I can look at this in terms of fractions. So my sequence progresses like this: 1 over 1, 2 over 3, 4 over 9. And so I can look at how I'm multiplying in my numerator and how I'm multiplying in my denominator, and that will help me also set up r. So if I look at this, 1 times 2 times 4, that would be multiplying by 2 every time. 1 times 3 times 3 again would give me 2/3. And then, like I said, since I know that it's alternating signs, my r is always going to be negative. So there's a couple ways that we could do this, and we'll talk a little bit more about this when we come into class. But don't be afraid of the fractions and still be able to find a way to navigate around them without having to worry about decimals. And so if I put this together, that my r is negative 2/3. So when I write my recursive formula, a sub n equals a sub n minus 1 times negative 2/3. So any term that I have before it, just multiply it by 2/3 and we'll be good to go. And so now that we looked at our recursive formula, which really just helps us build a list, we can move on to our explicit formula, which helps us basically to find any term knowing the first term, or a sub 1. So if I know the first term and I know what my common ratio is, so I can add r to this. So if I know what my constant ratio is, then I can find any term that I want to. So as long as I can find those two things, we should be okay. But let's write our explicit formula first. So the explicit formula, again, is going to kind of follow the same pattern, but it's just going to be a little bit different. So a sub n is going to equal a sub 1 times, kind of the same fashion. What we're going to do is we're going to take r and raise it to the power of n minus 1. So basically what we're going to do is, since we're multiplying repeatedly, we're multiplying, repeated multiplication is exponential form. And so what we can do is, we know that we're going to use this constant ratio a bunch of times, and that's basically like what we're saying is we're just going to make those exponents. But again, we don't want to double count the first term, that's why we're subtracting that 1. Since we have a sub 1, we take 1 less up here because we don't want to count too many terms. So let's look at our example here. We have negative 1, negative 6, negative 36, negative 216. In order for me to find my r very quickly, I can just take and divide two numbers that are right next to each other. So negative 6 divided by negative 1 gives me a positive 6. Now I could stop there, but that doesn't necessarily mean that this is going to be geometric. So I just have to take another set of numbers and just make sure that this works the same way. So r is equal to negative 36 divided by negative 6, which also gives me a 6. So that means my r is equal to 6. So I'm multiplying by 6 every time I do this. Now the whole goal of this is, if you look right here, that I'm going to find my 11th term. So the whole point of this is to use my explicit formula to find my 11th term. So what that means in terms of these variables and things like that n is going to equal 11. I want my 11th term. So as I plug this information in, a sub 11, so my 11th term, is equal to my first term, which my first term is negative 1, times my r, which is 6, so 6 to the power of 11 minus 1, or we could simply write that as a sub 11 equals negative 1 times 6 to the power of 10. And then I can go ahead and evaluate that. And so that gives me my 11th term of negative 60,466,176. So basically what I'm saying here is that when we use these geometric sequences, they can increase very quickly depending on whatever our common or constant ratio is going to be. So instead of trying to write all these out, we can use our explicit formula very easily in order to determine what those values are going to be instead. So basically just make sure that you remember and write down your explicit formula, and then just plug in all the information that you need. So find r, find n, and find your a sub 1, so that you at least know what those values are. You plug them in and just follow your order of operations, and that's how you can find whatever term that you need. Alright, so this last example is going to use kind of a combination of everything that we've done so far. So if we look at this, we're given a sub 1 is equal to 5. So again, what we're looking at here is that is our first term. We're given r is equal to negative 3, so that's our constant ratio. So we know at least how the numbers are changing. And so what I want to do is I want to write my explicit formula and then find the first 4 terms of the sequence. We can kind of do one of those, first and do the other one second, but the idea is that I want to build my sequence. So I can use my recursive formula, or kind of my intuition, to build my sequence. And so my sequence is going to start like this. Well, I know it's going to start with 5. I know that each time that I am changing from one number to the next, I'm multiplying by a negative 3. So this becomes 5 times negative 3, which gives me negative 15. Again, I could use my recursive formula for that, because I can just plug in a number and find out whatever the next one is. But like I said, we can use our intuition to do that too as well. Then I can keep multiplying by negative 3, which is now going to give me a positive 45, because negative 15 times 3 is going to be positive 45. And then my fourth term is going to be negative 135. And so the idea is I can just progress through that. Now one thing, like I said, to keep in mind is that if you notice that these signs are changing, your r value is always going to be negative. Because if you think about it, positive times a negative, negative times a negative gives you positive, positive times a negative gives you negative. So the only way that you can switch the signs like that is if you're constantly multiplying by a negative each time. And so from this information, we don't really need anything else to write our explicit formula, because we have our a sub 1 and we have our r. No one has told us what number of term that we want to find, so we don't have to worry about that right now. And so our explicit formula is going to start with a sub n. Since no one told us what term that we want, this is just a value, so we don't need to worry about it right now. And then we're going to do the first term, which is 5, times, and now I'm going to put this in parentheses. Now if you notice, we just have to make sure that we put this negative 3 in parentheses, because when we raise it to the power of n minus 1, we need that negative 3 to be in parentheses, because I'll show you this right now. Negative 3 to the second power is positive 9, but negative 3 to the second power without parentheses is actually negative 9, because it's saying take the opposite of 3 squared. Here it's the opposite of 3 squared, which gives us positive, but here, according to our order of operations, we always make that negative with multiplication, and so that always would come after we raise it to the exponent. So just be very careful with how you do this, and make sure that you always put your r in parentheses. That way you eliminate any doubt of what it's going to be. And especially with exponents, you're going to want to put things in parentheses when you're using that, so that you don't get the wrong idea. And so that's basically going to do it for geometric sequences. We can kind of find the parallels between that and arithmetic sequences, but the only difference is that we're using multiplication and division this time.